We've talked about histograms and box-Whisker plots. There are other graphical representations other than those that we still need to talk about. And in this video, we're going to talk about polygons of a variety of sorts. So here we have an example where we ask the question, how many blueberries are there in blueberry muffins? So we do a study and we get a bunch of blueberries and count how many blueberries are in each one. It's a fairly large study, so showing the original data list would be too long, so presenting the data in a frequency table form. We could create a histogram just to get a visual. That can be kind of nice. But the question is, we're not really doing histograms. We want frequency polygon. What is that? Well, what we need to do is, first of all, move our frequencies over. We need a little bit of space, because for a frequency polygon, we really need xy coordinates, and the x is going to be the midpoint of the intervals. So we actually have to get the midpoint, which is just the average of the ends of the interval. And those become your x-axis coordinates. And then the y is your frequencies. Our biggest frequency is 17, so I went up to 20. And you literally just plot the points like xy coordinates. This point, for example, is literally those coordinates. Then all you have to do is connect the points up with straight lines. We're getting close to a polygon because, of course, polygon has straight edges, but it's a closed figure, and this isn't closed yet. So what we need is to go one more interval beyond the 45, so 45 to 50. Well, how much data is in this range, this interval? Well, assuming that this original frequency table showed all the data, then the answer must be 0. And you can see that we now have this, it comes down to 0 onto the x-axis. We need something like that on this other side, so we need to go in front of this interval. So the -5 to 0, which would be before this one. And how much? 0 data, of course. And so we've come down to the axis again. Now the only thing left is to draw the line across, which I've just done. And what we have is a frequency polygon, or just, it's a polygon. It's a straight-edged, closed figure. So that's a polygon. Now, the next thing is there's also a relative frequency polygon, a slight variation. To get relative frequencies, we need how much data there is. 72 blueberry muffins were studied in this sample. I'm going to enter the midpoint and frequencies into my calculator, which you can see I have done right there. So I've put them into L1 and L2. And then to get relative frequencies, you just put in the formula L2 divided by 72, and you get relative frequencies, which are essentially percentages. You then graph them in a very similar way. The y-axis is now not frequencies, but relative frequencies, so you do have to change the scale. You go up to 0.25 in this case, because my largest relative frequency is 0.24. Right, and then plot the points in a very similar way, like those are just coordinates. Connect them up, including the zeros at the end, and you have a relative frequency polygon. Now, the question is, why would you use a relative frequency polygon instead of a frequency polygon? Well, that comes up if there was maybe a second study, like this one, conducted, maybe by someone else or maybe in a different area, and the frequencies are actually much bigger. There's a much bigger study than the original one. So if we try to compare the two studies by frequency polygons, it would be a little ridiculous, right? And it would be a bad comparison. It would be very difficult to compare these. But if we calculate the relative frequencies and create a relative frequency polygon, then that's actually quite a reasonable comparison. So relative frequency polygons are very helpful when you have frequencies that are quite different in scale. Now, the next variation on this theme is cumulative frequencies. Now, this is a little tricky, but really what we're talking about, and of course we can make a cumulative frequency, actually technically it's not a polygon because it doesn't go down to 0, but usually call them polygons. All right. And this is actually also called an ogive, special name. So you might hear that every now and again. So as we move down interval by interval, what we're going to do is, for this position, this is actually going to be the sum of all the frequencies, of that position and less. So in this case, that would be 3. Now, the next one is going to be 4 plus all the ones beforehand. So that's, of course, 7. And you're just going to keep doing that as you go down the list of all the intervals until you get to the last one. And notice that by the time you get to the last one, it's this one plus all the ones before it, which, of course, is all of them. So these two numbers should match. And then you're going to need to change your y-axis because, of course, these are now cumulative frequencies. It goes up to 72. So I have to retool that and make those up to 75. And so I scaled it kind of like that. And now you can plot the points. This is your x. This is now your y. And so there's your x, there's your y. Plot them just like that. And you get something that looks like this. Right? And it always builds. Right? Because, what would it mean to go down? It means you have to subtract something, but we're cumulatively adding, which means the frequency would have to be negative. And that doesn't make sense. How could you have less than 0 numbers in a particular interval? So it can be quite flat, but it never actually goes down. It always builds. It's always cumulative. So now we can go to the next obvious stage, which is the relative cumulative frequency polygon, which just means taking your cumulative frequencies and converting them into relative cumulative frequencies, which would be taking L4 and dividing by 72. And of course, that turns them into percentages. And it should make some sense. This last one is 1, which is 100%, because, of course, you're adding up all of the frequencies, so that's all of them, 100%. Again, you'd have to rescale your y, because now you're going up to 1. And it should always go up to 1, again, because this last number should always be the same as n. You graph it, and you put them together, and that's your relative cumulative frequency polygon. Right? And that is actually the same as percentile. The question is, why would you ever use relative cumulative frequency polygon? Well, this actually gives you, these are percentiles. Right? So you can pretty easily grab percentiles, and I have to be so clear. The AP exam tends to like to throw these every now and again at you. I'm going to jump back for a moment to here so that I can show you how to do this on your calculator. So first of all, let's remember that I have the data into L1 and L2. You can make a frequency polygon in your calculator. If you go second stat plot, right, we can go to our plot. And this first one, I'll do that one first. Just the dots is a scatter plot. Notice when I hit enter that this is going to change, because now I have both x and y for scatter plot, and it conveniently is L1, L2. Check my window settings. If I go from -5 to 55, that's going to be fine for this scale. And my y max is 20, perfect. So if I hit graph, there's my scatter plot. If I want to make a frequency table or frequency polygon, I can go into my type, and if I move over to here and change that, still on L1, L2, if I hit graph, all right, then there's my frequency polygon. Something else I should probably show you as well, a little bit different. If I want to use my 1 var stats with this data, it's a little different. You have to be careful because if I just do L1, 1 var stats L1, that's wrong. It will give me answers which are the wrong answers because it's, if you look, n is 9. Right, but it should be 72. Why is it 9? Well, because I just put L1. There are 9 numbers in L1. So it's just averaging those 9 numbers, which is not accurate. There are actually 72 numbers. So how do I deal with that? A cool little shortcut for something else, if you go second entry, it calls up the last thing you just entered, which is kind of convenient. So to give it frequency, I have to do L1, comma, L2, and then it's going to know that there are 72 numbers, and now we can see that n is 72. This is now an accurate mean of the data, and all this is going to be accurate, including the 5-number summary.